Hello, so this is question 20 of this SMO paper. So you can take a look at it and pause the video maybe. And in the next couple of slides, we'll discuss a solution. So we'll start with the walkthrough of this question. So I want to start by noting that you can see many trigonometric functions, and all of them take the form cosine n pi over 7, right? You see a cosine 4 pi over 7, a cosine 3 pi over 7, for instance, and you can think about it. And what we believe is that we need to simplify this expression using the compound angle formula or the double angle formula, for instance. Hello. So we'll continue the walkthrough of this question. So we start with the original question, right? And then what I first do is I look at the cosine 3 pi over 7 times the cosine pi over 7 term. And then since it's a product, I want to convert it to a sum. And the best way for me to do that is by the sum to product formula. And that's what I do. So the 4 cosine 4 pi over 7 stays the same, but then the cosine 3 pi over 7 times cosine pi over 7, I rewrite using the product to sum formula as such. Then what I next do is I multiply everything on the inside, and I get a 2 cosine squared 4 pi over 7 plus 2 cosine 4 pi over 7 cosine 2 pi over 7 minus cosine 2 pi over 7 minus 1. Then recollect from your trigonometry that 2 cosine squared theta minus 1 is your double angle formula for cosine theta. So 2 cosine squared theta minus 1 is equal to cosine 2 theta. So I use that fact in my next step to get the first and last term of the numerator of the fraction to be cosine 8 pi over 7. Then what I can then do is I can state that the cosine 4 pi over 7 times the cosine 2 pi over 7, it's a product, right? So I want to rewrite this as a sum, and I can do that again by the product to sum formula, right? And after I have done so, I notice that I can cancel out the cosine 2 pi over 7, and I am left with a cosine 8 pi over 7 and a cosine 6 pi over 7 term. Lastly, I combine this using my sum to product formula, right? And I get 2 cosine pi times cosine pi over 7. And then in the denominator, I have another cosine pi over 7. So what happens is these nicely cancel out, and I'm left with 1 cosine pi at the very end. And if you remember, cosine pi is negative 1. Why? You can just think about your diagram, right? Cosine 0 is 1, cosine pi over 2 is 0, cosine pi is negative 1. 10 minus negative 1 is 11, and when you square 11, you get 121. And that's how you do this question. So I want to take a couple of seconds to highlight the important things that we did here. So the important things that we did is we considered how to simplify the expression and get cancellations. And if you look through the steps again, it's basically applying product to sum and sum to product a couple of times. Then that's the main gist of this question. I mean, yes. Hello. So we'll be looking at question 21 of this paper right now. So question 21 is more of a number theory sort of problem, right? You have a big number and they're asking you what's the last digit of this. Now, obviously, you don't go ahead and try to find out what the number is. Just kidding. But yeah, you can take a look at this question, then pause it maybe, then we'll think about what to do in the next slide. All right, so here's a walkthrough. So I want to start by noticing that for questions like these, modular arithmetic is your best friend. What is modular arithmetic? Modular arithmetic asks you the question of, if you take some number, let's say 15 for instance, and divide it by another number, let's say 4, what's the remainder that you end up with? In this particular case, the remainder is 3. 15 divided by 4 is 3 with the remainder of 3, right? So modular arithmetic really asks you what the remainder of a number will be if you divide it by a particular base, for instance. So you realize that this number mod 10, which means what's the remainder when you divide by 10, that's the last digit, right, basically. So modular arithmetic will really be your friend in cases like these. So we can continue by looking at this. So we start off by noting that 2017 to the power of 2017 is congruent to 7 to the power of 2017 mod 10. So I provide a brief justification by the side, right? 2017 takes the form of 7 plus 201 times 10 to the power of some k, right? We know that using our binomial expansion, we can rewrite this. And after using binomial and rewriting this, since we're asking the question of what's the remainder if you divide by b, every term that contains at least one b, if you divide it by b, you're going to get some other integer, right? So the remainder will be 0, and all those terms die off basically. And because of your binomial series, you know that the only thing you end up with is your a to the power of k, which is your 7 to the power of 2017 in this case. Then from here on, we use a classic sort of trick. We start off by 7 to the power of 1, that's 7 mod 10. 7 squared is 49, but the remainder when you divide by 10 is 9. Then we can sort of repeat this down to 7 to the power of 4, and you get 1. Now here's the important bit. When you multiply this by 7 again, you're going to get 7 mod 10. And I claim that the pattern repeats. You can briefly think about this why. And essentially it's because once you end up with the 7, you know that the next term is going to be a 9, the next is going to be a 3, next is going to be a 1. And so you know that the pattern is going to repeat like this, right? So all we need to do is look at the pattern. Then I say that 2017, it's congruent to 1 mod 4, right? Which means that based on our pattern, we're saying that 7 to the power of 2017, when you look at the last digit, we're saying that it must be 7. So that's the core idea of what we're doing here. So you end up with 7 as your final answer. Then we can look at question 22, which I myself struggled with. So it asks you the question of how many ways 4 integers can be chosen from like a particular set such that the constraints are satisfied. The issue with questions like these that involve permutations and combinations is that sometimes they are a bit tedious. And that is unfortunately the case for this question as well. So you can pause now if you want to, but here's a walkthrough. Right? We need to resort to casework to some extent to consider this problem. So we can start off by bounding a1 from above. We want to choose 4 integers, and we know that the difference between each integer must be at least 5, right? So you know that the maximum value of a1 is 11. Why? When a1 is 11, a2 is going to be 16, a3 is going to be 21, and a4 is going to be 26, right? Any value of a1 greater than 11 is not possible. Why is it not possible? Because you can't satisfy the constraints and choose 4 integers at the same time, right? So the maximum value of a1 bounded above is 11, right? So now what we're doing is essentially casework. We know that a1 is between 1 and 11, and we're considering all these cases, right? We start with the cases from 1 to 5, where a1 is between 1 to 5. So how we're going to go about this casework is we know what a1 is. We're fixing it based on our casework, right? In this case, for instance, a1 is between 1 and 5. So we know what a1 is. Then we ask the question of what can a2, a3, and a4 be? In other words, we're essentially asking the question, what's the difference between these integers? How many possible differences are there? For instance, when a1 is between 1 and 5, any possible sort of combination of these differences work, if you get what I mean. Let's consider a1 equals 3, for instance. If the difference is 5 throughout, you're going to get 3 plus 5 is 8 for a2, 13 for a3, and 18 for a4. And similarly, if your a1 is 4 and your difference is 7 throughout, you're going to end up with 4 plus 7 is 11, then 18, then 25, right? So you realize that any sort of combination of these differences is allowed. And since there are 3 possible choices for each difference and you have 3 differences, what's going to happen is that you have 3 cubed or 27 choices for each A1, and since we're considering from 1 to 5, you have 5 times of that, so 5 times 27 for the case where A1 is between 1 and 5, inclusive. So then we proceed similarly, we consider A1 equals 6, right? For A1 equals 6, all the possible combinations are allowed, all possible combinations of the differences except one. And that case which isn't allowed is when all the differences are 7. Because notice, 6 plus 7 is 13, that's A2. 13 plus 7 is 20, that's A3. But then if you try adding another 7, you're going to get 27. That's outside our set, so it isn't allowed. So one possible set of differences is not allowed. So we're subtracting one possible case for this. And we can sort of repeat it throughout. And it's a rather tedious process, I might say. But we can repeat it for A1 equals 7, 8, and we're essentially doing the same thing. We're looking at the possible differences and their combinations and seeing which ones aren't allowed, right? And then after doing all that tedious work and summing it up, you find that there's 216 total ways. So the main struggle that one may have with this question is that you're not sure how to approach this. You might be thinking there's some elegant way. Whenever I do MO problems, I always hope that there's some elegant way to do it, that the question doesn't involve tedious algebra, for instance. But sometimes you need to understand that tedious work may be involved, especially for questions like these. You're doing a bit of casework. It's painful, but it must be done. But after you do that, you realize that despite it being tedious, it's quite simple, and then you can consider each case separately and then add it all up. Then we can look at question 23, right? Question 23 is probably the simplest of the lot that I'll be covering because this is a problem that you have probably seen many times. So you have alpha and beta as the roots of a particular quadratic equation, and we want to determine alpha to the power 4 plus beta to the power 4. There's this very famous theorem, Vieta's formula, that states the relationship between the roots of a quadratic and its coefficients, right? And this relationship is, I have given over here. The sum of the two roots is equal to minus b over a, where b is the coefficient of the x term and a is the coefficient of the x squared term. And likewise for the product of the terms. So how do you prove this, you might ask? Right, proving this is not actually a difficult task. You realize that a quadratic can be written as x minus alpha times x minus beta times some scaling factor, let's say n, and this is going to give you a formula for the quadratic based on its roots. Then you can multiply it throughout inside, and then you can simply compare the coefficients to what you have over there, and then you can end up with your Vieta's formula. So this is the best starting point. And based on Vieta's formula, you get alpha plus beta is equal to 7, and you get alpha times beta is equal to 11. So you get those two relationships. Now you look at what's going on over here. All right. To find alpha to the power 4 plus beta to the power 4, we do a bit of algebraic manipulation, basically. So notice that alpha squared plus beta squared is alpha to the 4 plus beta to the 4 plus 2 alpha squared beta squared. So you subtract away the final term, and then you just end up with the alpha to the 4 plus beta to the 4. For the inner term, you can essentially do the same idea again, and then you end up with the expression that's completely filled with alpha plus beta and alpha times beta, both of which you have the numerical values for. Then you plug it in, and you get your answer. So the key concept of these sort of questions, basically, is look at Vieta's formula, find some algebraic manipulations which get you what you want, and apply them. That's the key idea for stuff like this. Next, we move on to question 24. I particularly dislike this question because it is rather weird if you think about it, but yeah, you can pause it for a second, try to do it maybe. Then we start with the walkthrough, right? So I talked about a quick note at the side. I'll talk about that briefly. When I tried this myself, I was able to recognize that AN, that sort of sequence, it would be like a quadratic. Because if you look at the conditions that the question specifies, it basically says that the difference of like the an series is a constant. And I know that the difference of a quadratic is a constant. However, I was struggling to find the actual formula for an, right? But here it is. So you start off with the formula that they give you. Bn plus 1 minus bn is equal to minus 2. So you can rewrite that slightly, and based on a sort of recurrence relation, since bn is related to bn minus 1 and bn minus 1 is related to bn minus 2, you can sort of chain all this down and you can get an expression for bn in terms of b1. So that's your starting point. Then you go to an plus 1 and you look at the conditions that the question gives you. Bn is equal to an plus 1 minus an. You rewrite it slightly and then you get an plus 1 is equal to an plus bn. And you have a formula for bn that we just got above. So you can essentially do the same, you can essentially apply the same ideas here, and then you would get another recurrence relation, because an plus 1 is related to an is related to an minus 1. So an plus bn is going to be equal to an minus 1 plus bn plus bn minus 1. And if you chain this argument down, you'll realize that an plus 1 is really a1, plus you're summing all the bk's from 1 to n. Then you know the actual formula for bk from above, so you substitute that in, and then you can sort of simplify the expression within. If you have a constant term b1, you can just multiply that by n if it's inside a summation. Then you have a linear term. You have some n and whatever, and you can also simplify that, and you get the expression at the bottom. So then you have a5 and a10. They give you that in the question, right? So then what you have to do is you solve a set of simultaneous equations, and then you figure out what b1 and a1 are because of the relationships that you got in the previous slide. So after that, what you can do is, based on the relationship that you got in your previous slide, and since we know what a1 and b1 are, we substitute this back in, and we get a formula for an, which is very nice. And now we want to find the maximum value. And for maximum values, we always turn to derivatives. We take the derivative of this expression, and you realize that n is 50.5 when it's seemingly maximized. But we know that n has to be an integer, so we just manually check the floor and ceiling values of 50.5, which are 50 and 51. And after checking these, you realize that the maximum value is 2685. So the main challenge with this sort of question probably is sort of thinking about how you're even going to start. And now that I reflect upon it in hindsight, probably the best way is, since you're given a sort of recurrence relation, right? A recurrence relation is basically you have bm plus 1 is defined based on the previous term, bm. Whenever you have a recurrence relation, now I realize that it's probably best to express it in terms of the very first term in that sequence and then working from there. And then when we do that, we realize that it's not actually so bad of a method to get what we want. Then question 25. Again, this is one of the easier ones that we will do. So you can pause it now and try it. But I'll move on. So for questions of this type, he's asking the minimum number of socks he must draw. Minimum number means what's the number of socks he must draw in the worst case scenario, right? Worst case scenario. So the worst case scenario for this, you just need to use a bit of intuition and think about it. What's the worst case scenario for this kind of question? The worst case scenario is this. The person draws all 20 orange socks, then he draws all 18, that's a typo, all 18 yellow socks, right? So after he draws all of this, you realize that he still doesn't have at least 2 pairs of 3 distinct colors. 2 pairs, notice this. 2 pairs means 2 sets of 2, which means 4 socks. Then after drawing the orange, all the orange and all the yellow socks, he can draw 3 blue, 3 red, and 3 green socks. This is the absolute worst case scenario. But no matter what, in this scenario, on the next turn, whatever sock he draws, blue, red, or green, he will satisfy the requirements. So the minimum number he needs to draw is 48. So that's the sort of approach for these kind of questions. You just need to think about what's the worst case scenario and use a bit of intuition. Then we look at question 25. It's also a bit odd, I must profess, but the method is quite nice indeed. So you can pause it, maybe have a hand at it. But here you go. So for question 26, what we do is the absolute key bit is realizing what they're asking when they say even number of direction changes. And that key bit is realizing that even number of direction changes is equivalent to saying if you move right originally, you must end by moving right. Or if you move down originally, you must end by moving down. Why? Why is this the case? Notice that a direction change from odd to even or even to odd adds 1 to the total number of direction changes. So if you want an even number of direction changes, you're going to preserve what you started off with originally, right? And that's the key principle. So you have two possible choices. You start with the red dot and you end with the red dot. Why? Because you move right originally and you want to move right at your very last step. So that's one possible way. Or you move down originally and you end by moving down. Right? So that's what you need to figure out. So the problem essentially is how many ways are there to go from orange to orange using only down and right moves, because that's the constraint, and similarly for red. Right? So the insight is to go from red to red, for instance, you need to make a total of 5 down and 5 right moves. But the order in which you do them doesn't matter. So we simply sort of find the number of distinct ways we can permute this, and that's related to factorials, right? And then when we add them, we figure out the total number of ways we can do this. And that's how you do this. It's a pretty classic sort of combinatorics problem to ask you how many different ways there are for you to get from one point in the grid to another, given some constraints, but yeah. We move on to question 27, it's a Diophantine equation. I'm rather a fan of Diophantine equations because it's quite satisfying, really. So here's the question, and we'll do the walkthrough. So for Diophantine equations of this type, you have factorials and powers and all sorts of weird stuff, right? So for stuff like this, what we usually do is we consider the equation mod some value, right? You can experiment a bit over here, right? To gain an intuition for what mod you need to apply, you need to do a lot of problems. If you don't have that sort of luxury during the exam itself, you can just try a couple of different values. I tried taking this equation mod 3. It seemed promising because you have 3 to the power of m and 3 to the power of n. So I tried mod 3. I also tried mod 4 because you have a bunch of multiples of 4. But in the end, what ends up working is modulus 8. So you consider the equation modulus 8. And notice that for the factorial, since you have 4 times n factorial, for n greater than or equal to 2, the n factorial term will contain at least one 2. And that 2 multiplied by 4 will give you an 8. Right? So the 8m and the 4n factorial terms are both divisible by 8. Then you look at the 680 term. Right? 680, you'll realize is actually 640 plus 40, which is equal to 85 times 8, if my math is correct. I apologize. So you realize that all three terms on the right essentially die off when you take mod 8. So essentially the equation becomes 3 to the power of m plus 3 to the power of n congruent to 0 mod 8. But you realize that 3 to the power of x, you just consider some values. 3 to the power of 1 is 3. 3 to the power of 2 is 9, which is 1 mod 3. And so the pattern repeats. And 3 to the power of x is either 1 or 3 mod 8. And you realize that no combination of 1 and 3 gives you 0 mod 8. 1 plus 1 is 2 mod 8. 1 plus 3 is 4 mod 8, 3 plus 3 is 6 mod 8, but none of it gives you 0. So you realize that for n greater than or equal to 2, the solution has no integer solutions. So that's the beauty of using modular arithmetic. You can vastly narrow down your solution set. Then we can manually consider n equals 1. And manually considering a particular case isn't so difficult. So when you manually consider it, you realize that there's only one solution. N is 1 and m is 6. You just get that by manually checking. You plug n is equal to 1 over there, rearranging and finding out if there's any integer values of m. So after checking all that, you realize that this is the only integer solution pair to the equation, and since 6 is the only possible value of m, that's the sum of all possible values of m. So thank you, and that's my segment, and we conclude with the question on Diophantine equations. Thank you.